Hello, and welcome to this demo where we will explore the concept of liquid clustering, a powerful new feature that dynamically optimizes data layout in your Delta Lake tables to improve query performance and reduce costs. Today, we'll do an in-depth end-to-end demo and deep dive, generating sample data, saving it to managed Delta tables, applying partitioning, ZORDER, and liquid clustering, then finally benchmarking to see how liquid clustering measures up in practice. But first, let's look at what liquid clustering is, along with its benefits, when to use it, and when not to use it. Liquid clustering is a revolutionary approach to organizing data efficiently within Delta Lake tables. Unlike traditional partitioning or Z-ordering that require manual tuning and rigid static schemas, liquid clustering adapts automatically as new data comes in and usage patterns change. This helps maintain high query performance with minimal manual effort. The big advantages of liquid clustering lie in its simplicity and automation. Users define clustering keys based on query needs and let Databricks handle how data is clustered behind the scenes. It handles complexities like skewed data, high-cardinality columns, and constant data growth automatically. The incremental nature means you don't pay a heavy cost rewriting entire tables. Only new data is clustered as it arrives. Liquid clustering is ideal in dynamic, large-scale environments where query patterns evolve and data grows quickly. It works well when you have complex filtering columns or skewed datasets and want to avoid the maintenance overhead of manual partitioning or Z-ordering. It's particularly useful in modern streaming or real-time ingestion pipelines and supports concurrency. Now, it's important to keep in mind that liquid clustering is not a one-size-fits-all solution. It's not compatible with Hive-style partitions or use cases needing strict control over clustering timing. If your workloads depend on sophisticated multi-column filtering, Z-ordering may remain preferable. Also, you need to run supported versions of Databricks Runtime and Delta Lake to use it. Keep these limitations in mind when deciding. Okay, enough talking. Let's dive into the demo. First, I'm going to generate synthetic data that simulates real-world events. I'll create 1,000,000 rows with user IDs, event timestamps, and event types. Notice the event time is calculated carefully using timestamp seconds. This ensures each record has a unique event timestamp while avoiding errors from unsupported interval functions in Databricks SQL. This dataset will be the foundation for all of our tests. Next, I'm going to prepare the Databricks Unity Catalog environment. I'll make sure that the Lakeflow demo catalog and its bronze schema exists, and I'll create them if they don't. Then, I'll switch into the catalog and schema context so all subsequent tables are saved under the Lakeflow demo.bronze schema. This setup follows best practices for data governance and organization. In the next cell, I'll create a partitioned table by event type. Partitioning is a traditional optimization that physically separates data into folders based on distinct values of a column. While it can speed up queries filtered on the partition column, it may not be efficient for other use cases. This table will serve as our baseline for performance comparisons. Next, I'll write the raw data set as a plain managed Delta table without partitioning this time. I'll then run an optimize command with zorder by on user ID and event time. Z-ordering reorganizes data files to co-locate commonly queried columns, reducing the amount of data scanned during selective queries. It's a popular static clustering approach in Databricks. Now, we finally create a managed Delta table for liquid clustering. After saving the raw data, we enable dynamic liquid clustering on the user ID and event time columns via an alter table statement. Liquid clustering automatically and continually adjusts the data layout during table maintenance, adapting to evolving query patterns to improve future query speed and reduce costs versus static methods. Lastly, we benchmark all three tables with a simple select count star query, which performs full table scans. This unbiased test reveals how well each data layout optimizes scan efficiency. We time each query and print the results so you can see how liquid clustering stands against the traditional partitioning and ZORDER strategies for this workload. All right, that wraps up our walkthrough of liquid clustering in Databricks. The results reveal liquid clustering's adaptive advantage in organizing data efficiently over time. This dynamic optimization can help improve query speed and reduce cloud costs in real-world scenarios, especially with large and evolving datasets. Thanks for watching. Don't forget to like, subscribe, and hit that bell for more deep dives into modern data engineering techniques.